Portanto, as pessoas não indicam. Ok. Portanto, vou fazer a apresentação em inglês. Okay, thank you for the kind introduction. The title of my talk is Beyond 5G Communications. I'm planning to go through these topics. First of all, some information about fundamentals of wireless communications. Then I will go briefly through the fifth generation of cellular networks. Then I will address 6G and the evolution towards 6G, focusing on the research challenges from the radio and networking perspectives. So first of all, some fundamentals which are important for understanding what is 5G and what is coming next, 6G. First of all, in the wireless communications, we communicate using radio. Because of that, we use antennas, and these antennas, they generate signals and propagate electromagnetic waves. These waves, they have a frequency associated, and very important is that to this frequency of this carrier, of this wave, there is a wavelength associated, and this wavelength, it decreases with the increase of the frequency of the wave. This is an important fact, because then, and in order to generate these signals, we need to build antennas. And there is a direct relationship between the wavelength and the length of the antennas. For instance, a basic component of the antenna, that is that alpha wave dipole, it has precisely a length which is half of the wavelength. So that means that the higher the frequency, the smaller will be the antenna. Of course, then we compose and use sets of antennas in order to control the radiation diagram of these antennas. And we may put these antennas radiating more in one direction than in the other direction. And by doing that, we say that we are associating some gain to the antenna. But the point that I'd like to raise is that there is a relationship between the dimension of the antenna and the frequency that we are using. Another important topic is this one. The quality of the communications will be better if the power of the signal received is high. And it is well known that the power received for a given power transmitted decreases with the distance between the receiver and transmitter. So that means that in some way the power transmitted propagates in all directions, and the larger the distance, the larger the area of the sphere, and smaller will be the power received. And on the other hand, it is also well known that this power will decrease with decrease of wavelength. So that means that the higher frequency of the carrier that is transmitted by this station, the smaller will be the power received. So these two relationships are important because, in 5G and 6G, we are walking towards higher frequencies. That means that because of that, we are going to have wavelengths that are smaller, and we are going to have, for the same transmitted power, we are going to have cells that will be smaller and smaller and smaller and smaller. And for very high frequencies, we are going to be in a situation which is similar to light. So, you know, if I have a lamp here or a light, the light emitted cannot traverse, for instance, walls. That will be almost the same. So the higher the frequency, the smaller will be the ray of the cell, and the more difficult it will be for these signals to traverse obstacles or shadows. Now regarding bit rate, you know, communications is most of times about very high bit rates, and bit rates, the capacity of the medium, of the amount of bit that we can transmit, can be defined by a well-known formula, that is Shannon law, that says that the number of bits that we can transmit per second by a given transmitter, it depends very much, first of all, of channel bandwidth. A channel bandwidth is something which is different from the carrier of frequency that we have been talking about. But usually, the higher the frequency of the signal that we are transmitting, the larger would be the bandwidth of the channel. You'd say that this channel could be 150, 100 times the frequency of channel. So the higher the frequency that we are using, the larger will be the channel bandwidth, and because of that will be the bit rate that we can transmit. But this capacity, it also depends, and this is an increasing function, on the power received. So that means the higher power received, the higher capacity, the higher frequency, this one, that will imply that this band is higher as well, the higher capacity. Of course, that then we'll have also to consider interferences. And as you can see here in the picture, what matters is not only this power received, but it is relationship between power received and interference that we are receiving from other antennas that are transmitting on the same frequency. These two rules combined, that is that capacity that has this relationship with the power received, and then power received that has a certain relationship that we have seen that decreases with square, inversely proportional to the square of distance, makes that capacity to decrease very fastly along the time. So we may have very high capacities near the base station, but then this capacity tends to decrease. So knowing that, let me now try to address first the fifth generation of mobile communications. Let us try to show you how these systems work in general terms, and then I will address 6G, that is the next generation. First of all, the fifth generation of mobile communication is the one that is being deployed, and it has been designed in order to support a large set of use cases. That is, in opposition to what has happened to previous generation, 2G, 3G, 4G, in which the main objective was to increase the bit rate that we could provide to my mobile phones. Here in 5G, and for the first time, we started to define requirements which are different. That is, we start to design this communication system for a set of use cases that are very different in nature. For instance, of course, that we still want to transmit high-quality video, but the technology has also been targeted and designed, for instance, to support interactions which should be very fast. That is, communication between robots. They should happen with very small delays. And for instance, when controlling a machine in a factory, we should also have very high reliability for transmitting the information. So there are certain cases which can be classified under this class, ultra-reliable and low-latency communications. And also, we started to define use cases for this technology, for 5G, which enable us to get information for a large number of sensors. That is, the communication should also be able, the communication system should also be able to get information from sensors that should be sleeping a lot of time and should not, for instance, consume much energy. And so from that point of view, they are very different from a mobile phone. So all these use cases has made 5G to be designed not as a single communication network, but as multiple communication networks. Of course, that network that is being installed nowadays, we are, in this first phase, we are mainly having the network, a 5G network that addresses mainly mobile broadband, that will provide to you 100, 500 megabit per second to your mobile phone. But soon, in coming years, we'll start to observing, let me say, different trends of these 5G communication networks. From the architectural point of view, the 5G network can be described as shown here in the picture. First of all, and from below to top, we have what we call user equipments that in fact are the terminals that we use for communication. And that in 5G can be a mobile phone, can be a sensor, can be a robot, can be a vehicle, something that needs to communicate to the mobile communication systems. Then we have the radio devices, that is those base stations that you see, for instance, on top of buildings. And those that I'm going to call it G-Node B, it is the name of the standard. It is a kind of radio access point to which these mobile terminals attach and communicate. It's a kind of Wi-Fi access point that you know. These equipments, they have radio associated, they have channels in which they provide communications. And they are also in charge of scheduling terminals. That is, these terminals, if we have multiple terminals associated to one of these base stations, this node that will say, this is your time to communicate, this is your time, this is your time. So the scheduling of this equipment so that they can transmit information, packets, will be done by this G-Node B. Then we have also an important function which is done in a cooperative way between different G-Node Bs. That is that one of managing the terminals. When the terminal is active, for instance, involved in the voice communication, and it moves, the communications, because there is a limit for communication, will have to be changed from one base station to the other one. The management of this mobility is made by these Node Bs in a cooperative way. And of course, with the help of user equipment that will inform the system that it is receiving a low power signal, and then it needs, probably it should be better to move to another G-Node B. Then we have the core network. So these equipments, they are the radio equipments. You know, this is the air interface. And then they are connected to other equipments that are usually in the office of telecom operator. And in this location, which you call the core network, there are two main important functions. The first one is that one which you call the access and mobility function, that basically is in charge of authenticating the terminals that enter into the network. So instead, in 5G and 4G, instead of using a username and password, we use the credentials that are stored in your SIM card, and that information is passed, and it is validated on this access function. But also here, for terminals that are not involved in communications, that are not active in transferring files or in phone calls, this entity has to have a register of the location of these terminals, so that, for instance, when a new call arrives, the system knows where the terminal is and can deliver the call through the G-Node B to which the user equipment is attached. So those two functions, access control and location management of idle terminals, are important things. Then we have another equipment that we call the user plane function, and it is a kind of router to the internet. That is, for instance, it is a kind of Wi-Fi access point and this is a router that connects to the internet, and it has also a set of functions. First of all, it makes the interface to the internet, of course. Then there will be a kind of tunnel established between this router and each of these equipments. And based on this tunnel or on a set of tunnels, we'll be able to send traffic by giving this traffic different priorities or different guarantees in terms of delivering the information and losing the information. And so this is, in very simple terms, the architecture of a 5G network. In fact, this architecture is a little bit more complex. You know, this is what here I'm representing the IMEF, access and mobility function. And in fact, instead of a single function, we have a set of services that we call functions that are a kind of functions or microservice that can be deployed anywhere, and that enables the management of this network to be done in the very detailed and precise way. We are not going, of course, through all these functions, but this is just to let you know that we have them. And we have here two different views of these functions. One of them is that one which is related to the control of the system, and that one are these functions which are very much related to transference of the data. So from ear to ear, from the user equipment through the radio access network, the router, the user place function, until the internet, we have packets which are exchanged. And then we have another set of functions, which you call control plane, that are in charge of controlling the, let me say, the communication system. Coming back, 5G is working on two ranges of radio frequencies. The frequency range number 1 and number 2. And this first is operating from frequencies which go from 450 megahertz up to 6 gigahertz. The second one will go from the 24 up to 50 gigahertz. Currently, what we are using in Portugal for 5G is the first range of frequencies. And for instance, these have been the lots that we have had in the auction that we had recently finished in Portugal. That is the telecom operators that got these lots. They now will start operating in these bands, in these channels, and here you can see the bandwidth of each channel. There are bandwidths of 5 megahertz, 25 megahertz, and so on. In next years, or next year, very probably, we are going to have a second auction for this range of frequencies, but of course here we are going to have, let me say, a different way of radio communications. We are going to have smaller cells, but cells that will provide much higher bandwidths to the equipments that transmit. Important as well is this new characteristic of 5G. In the way which is different for what has happened in previous generations of communications, in which we had dedicated equipment for each of the function of the cellular network. Here, and for the first time, we are going to have 5G defined as a set of functions. And these functions will be able to run in standard computers. That means that the 5G and 6G network of the future, it will consist of, let me say, of a data center, having computers, which are having connections, very probably optical fiber, to antennas, and in these antennas we'll have very basic functionality. We may have only functionality just to generate the electromagnetic waves, and most of the functionality that we need, for instance, to get the bits from the carriers, from the radio signals, they may be implemented here in the cloud. And not only the radio functions, but also all these functions I have seen before. That is, the communication network is being more and more virtualized, and from the infrastructure point of view, it is becoming very simple. And that enables us to create a new kind of networks that are a kind of logical networks that in some way are very similar to the virtual machines that you can create on your computers. That is, if most of the function can be put on computers, then in these computers, I can, or in a set of computers, I can create a kind of virtual machines that will be used to create virtual networks, and then I will be able to create a virtual network for each type of application. We call these virtual networks, we call them network slices. And we may build, for instance, a network that is designed for mobile broadband, for multimedia. We may have some other one, for instance, for connecting cars. We may have some other one which is dedicated to industry and so on. And each of these slices, each of these virtual networks will be in the same way that you create virtual machines in your computer. We have to associate CPUs and memory. Here it will be the same thing. For each slice, for each virtual network, we'll have to associate memory, CPUs, but also radio, the radio channels that will be used at radio station. So it will be very easy to create on-demand new networks that are given to a certain entity or which is designed to support certain types of traffic. And this is a kind of revolution on telecommunications field. And that, for instance, enables us to, I will not go through all details in this slide, but that will enable us to define a kind of networks that include private networks. That is, nowadays 5G does not enable a company to have its own 4G network, but in 5G it will be possible that a given company can have in its installations, in its location, a network which is fully dedicated to each activity. There are several, let me say, ways of doing that. And basically what they consist in looking at the important components of the network and decide if these components, these functions will be located in the telecommunications operator location, or if they will be located on the industry or in the company location. So it will also bring a new way of looking for communication network, because for the first time, for instance, a given industry may have, let me say, a wireless network which can provide guarantees of quality of service, because there will be no interference as we have, for instance, in Wi-Fi at home. And by having this, by having the assurance that there is no interference in the given location, for instance, an industry can control the robots, can control the machinery, because we have the guarantees that there will be quality of service when transferring the information. The evolution to 6G. 6G will be the next generation, and it will appear by 2030. This generation, they tend to appear every 10 years. And the requirements of 6th generation, they are currently being defined. But the aims, the objectives is to increase, let me say, the capacity of network manifolds from most of the perspectives, both from capacity, the user experience data rate, the delays, the number of devices supported, the location accuracy. So there is a large ambition, and let me say, 6G or 5G will see its capabilities increases typically by 10 times. So from our perspective and from perspective of the networks that we have nowadays, it defines an almost ideal network in the sense that we can provide terabit per second by doing that, and we'll have delays for transferring information that should be in the order of 1 millisecond. And then we'll potentiate a set of applications that are difficult to imagine. For instance, something which is often discussed is this Internet of Senses, in which we can provide information besides sound and vision, and will enable us to interact in real time with some other objects. Holographic communication, for instance, virtual reality, very high holograms and so on, they may be also potentiated because there will be wireless communication networks able to transport all this information. This thing also is important, and it is very much related to what is called nowadays the digital twin. That is, we may have a person, a human, interacting with a machine, but also we may have, let me say, holograms of people, of things, of machines appearing in front of us, and we may interact with them. But also we humans, we may be able, for instance, to enter with our own senses for instance, in the game, in the software game. And by doing that, we may establish what we call the digital real continuum, and things, reality and virtuality will tend to disappear and be a single way of interaction. And also communications with robots or between robots may also be potentiated because we have these two characteristics. Again, for 5G, the technique that is being followed for design the technology is very similar to what is being done for 5G. We are looking for different business activities and try to understand what are the new applications that we can have if we have this capacity available and this type of network available. And so we are defining use cases for each of these business activities, which you call verticals, and based on that, let me say, on this use case, we are starting to define requirements that for each of the applications, for each of the verticals, which of course consist in a set of applications, of foreseen applications, and let me say, performance indicators or objectives or requirements, performance requirements are being identified that then will be used to help designing the communication network. Let me now just try to discuss with you some of the challenges, some of the things that need to be researched in order to let the sixth generation of mobile communications be implemented. First of all, I'm going through the radio challenges. You know, in order to provide terabit per second, we will have to communicate at terahertz because higher frequency provide high channel bandwidths, and high channel bandwidths enable us to communicate, to send more bit per second. But as you can see, the attenuation or the distance at which the communications can be done decreases very much with the frequency. For instance, if I measure the attenuation, that is the higher the attenuation, the smaller the communication distance in dBs per square meter, we can see here clearly that, for instance, for 1 terahertz, the attenuation will be much higher than the attenuations we have nowadays. Nowadays, if you recall, we are 5G operating in 1 gigahertz, 3 gigahertz, and in the future 30 gigahertz. So the attenuations here are much smaller than the attenuations that we are going to observe here in very high frequencies. So from the radio perspective, a lot of research is required for understanding how to transmit information, and for instance, electronics is required for that. In these bands that go first, the upper millimeter wave band, which goes from 100 to 300 gigahertz, which is something which is below the 10 dBs per kilometer, and then how to communicate above these 300 gigahertz, in which the attenuation is very, 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 very high. And that means that we need to develop electronics which are able, let me say, to equip the radios that are going to have very large bandwidths. We don't know yet how to do that, and this technology needs to be done. And of course, we may also have to combine channels that are operating at different frequencies in the spectrum. That would enable us, as we have seen, to develop new kinds of applications, which we call these data-hungry applications that we have already discussed, such as augmented reality, virtual reality. This terahertz communication may also be used, for instance, to implement long-distance communication links. You know, nowadays, in order to support high bandwidth communication, we use optical fibers. But now in future, we may have, for instance, equipment that is flying or that is a satellite or something like that. So in order to enable the communication between these equipments, we may have this kind of optical links or links operating at terahertz, which enable us to transmit terabit per second. But of course, they should be very, very much focused. These are a given application. This is an application for this type of technology. And research needs to be done for that, for instance, on controlling the direction of the antennas that we are going to need to do that, because we have to have this transmitter and receiver antennas always well aligned so that we can enable communications. Then there is something that is also very important. That is because radio equipment will start operating at very high frequencies, they will be able to start working as if they were radars. That is, a base station, when operating at these very high frequencies, that has also large bandwidths, will be able to send pulses like a radar and receive echoes of the environment which is around. That means that the base station will be able to observe everything that is around. And that is a very important thing, because this base station, besides communicating, it is able to observe buildings, trees, persons, and so on, and to take advantage of it to, for instance, to locate people that is communicating, to see obstacles and try to find another solution to avoid these obstacles. So this is something that will be done, combination of communications and sensing. And same for terminals. When terminals communicating by using very high frequencies, these terminals, by sending these signals, will be able to see your hand, to see your gestures, to see your face. And by doing that, the sort of applications that will emerge or that will be able to be developed will be of a very different nature, because now we can develop applications that can transmit lots of information very fastly, but also applications that can see everything that is on neighborhood. And that information can be combined, of course, also with video cameras that we still have, but a new set of applications that we cannot imagine, but they will be a revolution again, will appear. And for instance, you can see how this can be put on cars. If we put these equipments on top of cars, so communications between cars and cars using these antennas to see what is around can be done. There is people that is saying that by using only communication systems, we can avoid sensors. So these sensors that nowadays we are putting everywhere, maybe we could, with these communication systems, try to get all this information, because we can see, but we can also have echoes that can provide us information about temperature, because the echo will be on a different nature or humidity. For instance, our colleagues that work on optical fiber, they do fiber sensing for many years. So all these techniques can now be put on radio as soon as we go up in frequencies, and the communication systems will be a communication plus sensing system, and that will be a revolution. So research questions on radio. These are a few, but if you like research, maybe you can go through some of them. Models for channels. What are the best bands for communication above 100 gigahertz? What is the difference between electric and photonics, since frequencies are advancing and are starting to be close to photonics? How much power can be generated? How to control the direction of radiation of the antennas? You know, in the future, these antennas, we are not going to have simple antennas. We are going to have hundreds of antennas elements. The antennas will be very, very small. It will be millimeters. It will be like the chips of a CPU. So lots of them. And these antennas, they will form beams for different users. So there will be a beam for you, a beam for you. And when you move these beams, moving in the same way that, for instance, when I point, let's assume that I'm sending communications to destination, then there will be a set of lights following all the user and all the robots, all devices. So the way at which we are going to manage the access of terminals to the communication system will be made in a very different way, and we should take advantage of the full control and detailed control of these antennas. And then, of course, how to enable the communications or the coexistence between communications and sensing. Now let us go to networking. From networking point of view, we foresee that this service-based architecture that consists in a set of functions that are a kind of web service that can be deployed everywhere on the internet. So, you know, these functions, we have studied only that, but there are a set of functions that we need to operate the communication networks that can be placed anywhere because they run in standard computers. So very probably we'll continue having this service-based architecture, and this is very good because it enables us to look at different ways of building private networks, and we may also develop new business models in which different actors may be part of the communication network because they can attach very well from the communication network functions and new ways of combining applications, business from the verticals, and the communication networks may be defined. So the functions of the communication network will be integrated in the universe of services that are nowadays around the internet. So things will be much more interconnected. But then here on the user plane, which is related to the function that transfer data from the user equipment to the network, some things also have to be done. For instance, this radio functionality, this routing functionality that we have seen before, nowadays they are not yet fully decomposed in services. They are still equipments that do these functions, and so we should look inside of these blocks and we should decompose them in services so that we can better allocate them to different locations. Another important thing is try to keep communication networks simple from the operation point of view. I don't know, for instance, if you have know-how about computer networking, but usually communications is done in layers. So we have 5 layers, but in communication, in 5G and 4G, the number of layers that we have for communication is very, very, very high. And for instance, this is the communication stack that you have at your 5G mobile phone. And we should be able to reduce this complexity and very probably we should do something so that it can approach it to standard TCP/IP stack that is, for instance, implemented on Wi-Fi stack, and this is something that needs to be done. Of course, there are reasons for things being like that, and most of them they are business reasons, so that markets can be protected. But this is something that needs to be done. Importantly is quality of service. Usually, the quality of service that you provide over wireless network is a stochastic quality guarantee. That is, we may guarantee that, for instance, 90% of packets will have a delay smaller than 30 milliseconds. But you cannot guarantee that all the packets will have a delay smaller than a given value. But for certain applications, such as controlling robots, vehicles, machinery in an assembling line, we need to send information controls for robots that should be precise, that you cannot lose, and that should arrive in the given instant. So we should be able to design the communication network so that for a certain and selected packet, we can guarantee 100% in a deterministic way that these guarantees can be done. So this is very difficult to be done, and research on that topic is important as well. Also, there is something that is a trend, and in which, for instance, in INESC, we do a lot of research, and that is related to the enabling the communication network, the wireless communication network, to be itself mobile. Not only the mobile phone, but overall infrastructure to be mobile. That is, those base stations that you see on top of buildings, why not to put them on a UAV or on a satellite, on a top of on a vehicle. So the mobility of the communication infrastructure as a whole is very important, and particularly in this type of networks, which you call non-terrestrial network, which consist in satellites that may be not very high altitude, they may be non-stationary or high altitude platforms, or even UAVs. So there is a new network emerging which enables us to combine the flying or the high altitude communication infrastructure with infrastructure that we have on field. And in order to be possible, we will have to make these functions, the mobile radio access network and mobile router, to be mobile and to be flying as well. And of course, we should be able to define or develop functionality for support a large number of handover. Handover is what is happening when a mobile phone is moving from one node B to the other node B. Now the cells will be very small. If we have these cells operating at the upper millimeter wave or at terahertz frequencies, so cells will be very small. And so because we are going to have more and more devices communicating, if they move, or if network is moving, they will have to, let me say, to change very often and in large numbers. And so we don't know yet how to do that. So how to support massive handovers is a challenge. Then we have this new concept that we are also starting to explore, that is the combination of vision and communications. For certain frequencies, or very high frequencies, we cannot communicate with nodes that are, for instance, on the other side of the wall, because all introduce very high attenuations for high frequencies, and so our communications cannot traverse the wall. And in some way, communication is limited to what we can see, because if we cannot see our partner, that means that there is an obstacle, and the ray that I'm using to communicate, a ray like this, will not traverse that. So trying to combine this capacity of using cameras to observe what is happening and take advantage of it for communication is something that is also important and that we are starting to explore. And this topic is also important. That is, machine learning is emerging everywhere, and important is that this machine learning will also start appearing on what we call edge devices. That is, all device, all sensor, all the control systems, sooner or later will have not programs as you are used to do, but will have a kind of neural networks for deploying in a fast way the function that they have to do. Of course, that these networks will have to be trained. Distributed systems will, in a distributed way or in the cooperative way, will learn, but after learning, they will have not programs written in C, but they will have neural networks operating. And we think that in the future, probably what we are going to have is not CPUs, but distributed brains spread around the world. And so these brains, to communicate, will have to exchange information. The information is that information that characterizes neural network. And the communication between brains will have to be supported by wireless communications. So what we may observe in the future is that the content of my brain, and not my voice and not my image, is transferred to some other place. And so new types of traffic, new ways of transforming information is sensed. That is, we are not going to transmit the information for senses, but brains will have to communicate directly. And by doing that, we have to build communication networks to support this type of new traffics. And in fact, you know that there are research going on this topic. So key questions relate to 6G networking, which we could explore if, for instance, doing thesis with at INESC-TEC, at networking group focused on wireless networking. So how to improve the user plane of 6G, how to simplify this user plane, how to put the 6G flying in the sense that we would like to have these functions deployed on top of, let me say, devices that can move, how to provide guarantees to certain packets and to some traffic, how to support massive handovers, how to combine vision, or at least take advantage of vision and sensing for communications, and how to start supporting these new types of traffic that are emerging. So these are things that will have to be done for 6G. Some of these topics are in some way being developed at CTM. And so these are topics that are, let me say, that seem to me relevant. And I would finish here my presentation, concluding, and these conclusions are a kind of motivation for those of you that enjoy and would like to work on telecommunications. The telecommunications still is a field full of opportunities. We have been able in the past to let me say, to provoke us a lot of revolutions since the old telegraph until 6G. Many ways telecommunications have been able to change the ways the humanity works. Each of these things have been a big revolution. And with 6G, as a continuation of mobile phone, we are going to see, let me say, communications enabling a set new forms of applications and new forms of operation that may transform the way that humans interact and the way that humans interact with robots, and the ways of robots will be interacting, and the ways that you are going to mix reality with virtual things. So telecommunications will enable that, and again, it will make another revolution. So I'd say that there are plenty of research and business opportunities as well, because those that are able to see it first will be able, if they would like to develop their own business, they will be able to, let me say, to take advantage of it and do that. And so I would conclude with this final sentence. So telecommunication will continue driving the future. So there are plenty of opportunities, and that's it. Thank you. Okay, thank you.